Welcome back to another tutorial. This is Mr. Holsey of A Squared Sufficiently Understood Science, and today we're going to be taking a look at the first of Newton's laws of motion, the law of inertia. This is the first in a three-part series where we'll be discussing Newton's laws. Now, before we get going, let's review what force is. So force is the cause of motion. It's what causes objects to move. Without force, nothing's moving. And we're going to learn that definitely for sure when we look at Newton's first law. And there are two types of forces, either pushes or pulls. An object is either pushed or it's pulled. A force is exerted for motion to begin. Now, forces are measured in newtons. And so this is the SI unit of force, and its symbol is N. It's measured using what we call a spring scale. This is what we used in our experiment not too long ago in class, where we had the electronic spring scales, and then we had the little tube things that you're holding the weights off of. Those are called spring scales. And so these are going to be measuring the amount of force an object is exerting. And so spring scales basically work by having an object pulled down on a spring, and it'll tell you how many newtons. And there are two types of forces that I want to talk about really quick just to make sure we remember it. Balanced forces and unbalanced forces. So a balanced force is where all forces are acting on an object, and all forces acting on an object are equal. Okay, it means there is no motion whatsoever. It's not moving. Now, when we say balanced forces, another way of looking at it is if the forces are balanced, nothing's changing its motion. Now, unbalanced force is where one or more forces acting on an object are stronger than the other, and therefore we will see motion. So you can kind of think of balanced and unbalanced. A simple way is a game of really poorly drawn tug of war. Okay, and so if we have a balanced force, so this person here on the left, let's say it's pulling with 100 newtons of force. This person over here is pulling with 100 newtons of force. This middle area of the rope is not going to go anywhere because it's a balanced force. There's no change in motion. But if this guy over here on the right suddenly gets tired, now is pulling at 50 newtons, the force is now unbalanced, and this is going to move over in the direction of the stronger force. And so this person right here is going to lose, and this one is going to win. So let's talk about Newton's first law, the law of inertia. So Newton's law of inertia states, every material object continues in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. Yeah. Let's try it a little bit more simply. An object at rest will stay at rest. An object in motion will stay in motion. It's not going to change on its own. So if you're listening to this at home right now and you're sitting at a table or in your room or just basically anywhere at your house, you'll notice that there are objects at rest everywhere. They're not just going to randomly start moving. Okay, they're going to stay at rest. That's their natural tendency. And if an object, and so if you apply a force to anything, it's like a cat knocking over a water glass. That water glass didn't want to move, but that cat made it move. So an object in motion, though, will stay in motion unless acted on by an outside force. And so that kind of explains why you have things in outer space that will just travel forever and ever and ever. So let's think about that for a second. An object in motion will stay in motion. An object at rest will stay at rest unless it's acted on by an outside force. So if you're in a car, you may not feel like you are in motion, but you really are. You're traveling, let's say you're going down I-10 going 60 miles an hour. Your car is going 60 miles per hour, and so are you because you're in that car. And so an object at rest will stay at rest. An object in motion wants to stay in motion. Oops. So Barbie here had an unbalanced, had a force that balanced her out. But Ken was an object in motion. He wasn't wearing a seatbelt. There was no outside force acting upon him. Therefore, whenever he hit the bumper, he just flew right off because he was still in motion. Barbie, on the other hand, she was in the same amount of motion as Ken. Let's just call this equated to 70 miles per hour. Okay, in a car. Barbie's also going 70 miles per hour, right? And so that means she has a certain amount of force that is pushing her along. And when they hit this bumper right here, Ken didn't have anything pushing in the opposite direction. So he didn't have a seatbelt on. But Barbie, as you can see, is strapped down to the cart. And so whenever she hit this wall, those straps pushed with the same amount of force in the opposite direction. Now she leaned forward because her body wanted this to go forward, but those straps kept her from going off the rail. So always wear your seatbelt. So an object not moving will not move unless an unbalanced force acts on it. It's kind of like saying homework will not get done on its own. Your room's not going to magically clean itself. Those objects have to have something act upon them for them to move. This ball will literally stay here forever and ever and ever unless something finally comes around and hits it. The wind blows, there's an earthquake, something. Some kind of unbalanced force has to happen for this ball to move. So objects in motion, those with velocity, will stay in motion. An outside force can change its speed, velocity, or direction. And so if it's changing, remember, any change in velocity is going to be acceleration. So we can also change the acceleration of an object this way. And so, for example, here you have a goalie who is deflecting a puck heading towards the goal. He's exerting a force against the puck. So the puck is coming in like this. All right. The goalie is exerting an opposite force, an outside force against the puck in a different direction. So the puck's likely to go off at an angle. But he's exerting an outside force. If he didn't exert this outside force, that puck would go straight, I'm sorry, that's terrible, straight into the goal. It wouldn't change its direction. But you're probably saying to yourself, Mr. Halsey, what makes things slow down on their own? I mean, things just can't go forever and ever. Unsubscribe! Yeah, so I get it, Jimmy. But there are other forces you have to take into account. So if in a vacuum, like space, for example, if you were to throw an object in space, as long as it didn't come in contact with anything else in the entire universe, it would go forever and ever and ever at the same rate, never slowing down, never speeding up, never changing directions. Inertia would just keep it going forever and ever and ever because an object wants to keep moving. If it's in motion, it wants to stay in motion. If it's at rest, it wants to stay at rest. But there are two things that slow things down on their own. The first one is friction, and the other is gravity. This is why when we throw a baseball or something like that, it goes towards the ground. It even slows down as it's reaching someplace because of friction from the air resistance. Whenever you walk across the ground, it's friction and gravity that slow you down. So Newton's law of inertia also has to deal with mass. So mass is the amount of matter in an object. Now, we're going to cover this in a lesson a little bit later, but mass and weight are not the same thing. Mass is not weight. We'll discuss that next time. But mass is the amount of matter in an object. The more mass an object has, the more inertia the object has. In other words, compare it to rolling a marble across the floor. Okay, you roll this marble, you can easily stop this marble with your foot. And I'm just going to write foot because I can't draw a foot. I'm not even going to try. But you could easily stop a marble with your foot. Now, what if instead we put a more massive object, like a bowling ball, and we rolled it across the floor? Is your foot gonna be able to kick it and stop it? Probably not without hurting yourself. So bigger objects are harder to start and stop. The more mass an object has, the more resistance it has to being moved. And so that's why it's easier to push something small than it is something big. Like pushing a bike versus pushing a Ford F-150. Or pushing my little tiny car versus a Ford F-150. So the more mass, the more inertia. So just kind of bringing this back up, friction. So friction is the force that acts to resist sliding between two touching surfaces. You can demonstrate this right now by yourself. Take your hand and run it across the table. You will feel friction. You will feel friction between the two objects. Take any round ball or anything like that, roll it gently across the table. If it weren't for friction, that ball would continue going all the way across the table. But if because of friction, depending on how smooth or rough the surface is, that ball's gonna either slow down fast, will eventually stop. And so the more friction, the faster it's going to slow down. The faster it's going to act in the opposite direction. So we have our motion, okay, and our friction is our outside force. And that's going to do it for Newton's first law of motion, the law of inertia. Make sure to join us on our next tutorial for Newton's second law. And this has been Mr. Holsey for A Squared Sufficiently Understood Science. Remember to like, share, and subscribe, and click that bell notification to know when we post new tutorials. See you next time.